Then. Okay, thank you all for coming, and thank you, Rima, for talking. So we're extremely happy to have, extremely happy to announce Rima Alaifari as my colleague and talking at 1W-MINDS seminar. She's going to give our seminar today. Rima did her undergraduate in Linz and PhD with now it's my now my notes ran away from my screen. So I guess yeah, this is so she did a PhD with Ingrid Aubéchis and Michel de Vries in Brussels, and afterwards she was a postdoc in ETH Zurich, and now she's a professor with the Applied Math group. And she's been doing extremely interesting work related to phase retrieval and different settings of phase retrieval. And very happy to have her speak to us about more work in this direction today. Rima, the floor is yours. Thanks so much.
Thank you. Thanks, Afonso, and thanks, for having me and for showing up. Yeah, so today I would like to a bit like recap the last few years of working on phase retrieval. I hope I can give some overview, at least from my perspective. I will not, of course, cover everything that has come up in the last few years in phase retrieval. And what we've been working on mainly is the deterministic setting. So we actually know the frame we're working with. So we have typically measurements that come from a short time Fourier transform or from a wavelet transform. And we ask the phase retrieval question, which is, what if we have lost the phases of these coefficients? Can we still recover the signal? Yeah, so I would just very just give an overview. So in principle, we're having an image reconstruction problem. So we're given some measurements. We would like to recover a signal or an image. And from an inverse problems perspective, typically we can model the measurement acquisition. So we have a forward operator A, and we're given some right-hand side G that we would like to, that we use to actually recover F. And the three main questions that we ask in inverse problems are, well, does the solution exist? Is it unique? And is the recovery stable? Stability meaning a continuous dependency on the right-hand side G. Why is that so important? Because if we actually measure something, then we won't know the exact G, but only a G delta. And maybe, or hopefully, we're given some noise level, which means like how good are we, how close are we actually to the actual exact data. So this delta we would call the noise level, and we would like to have some guarantee that also our reconstruction is close to the truth. Otherwise, the reconstruction, of course, is meaningless if we know that we have measurement error anyways. So, and inverse problems, we would mainly focus on these two questions, uniqueness and stability. These are the two that bother us the most. And that's what I would like to speak about today in the context of phase retrieval. Of course, ill-posed problems, they come up a lot. There are just some examples. So audio and X-ray diffraction being related to phase retrieval that I'm going to speak about today. But there are other applications, of course. You all know medical imaging being very, prominent for ill-posed problems, but also astronomical imaging, where you also have like a tomography problem, and maybe more fun is character animation. If you want to do it physics-based, then essentially what you're trying to do is to estimate parameters in a PDE. So it's a nonlinear inverse problem. And what we would like to do in inverse problems typically is to regularize. So we know that we don't have stability. So actually the set G delta is too large for us, meaning that being like satisfying the data well enough doesn't tell us that we're close to the true solution. We have a huge set. And what we typically do is to impose some prior knowledge. We say, okay, actually, maybe I know something about my solution to make this more tractable. And we say that we have regularized the problem if, as the noise level delta tends to 0, also the diameter of this set will tend to 0. So the better my data, the better my reconstruction should also be. That's the goal. That's what we would call a regularization. So Today I'm going to talk about phase retrieval. This has been work over the years with quite a few people. My PhD advisor and my postdoc mentor, Ingrid Doveshi and Philip Gross. Also two students of Ingrid, Rachel Yin and Gaurav Thakur, who are very successful in industry now. And my postdoc, Francesca Bartolucci, and my PhD, Matthias Velosov, more recently. So yeah, just want to mention all of them, and it's been fun working with all of them. So what is the phase problem? Maybe most of you are familiar with it. I will still try to give you some overview. First of all, the origin of the phase problem can be, well, traced back to X-ray crystallography, where it was discovered that actually when you have a crystallized molecule or a crystal, if you shoot an X-ray beam at this crystal, then the X-rays will diffract and they will give you meaningful information out of the diffraction pattern. So this diffraction pattern will consist of varying dot intensities, and they can be related to the magnitude of the Fourier transforms, essentially. And that reveals the structure of the molecule. Okay, so what one would like to have is the electron density F, but what we essentially get is something related to the Fourier transform magnitudes. So F hat absolute value, and one asks, okay, what can we say about the recovery? More modern is coherent diffraction imaging. So in coherent diffraction imaging, one deals with the problem of having something that is not a crystal. So a structure that one would like to image, but that is either a molecule but that doesn't crystallize, or just something that is not organic, another nanostructure. So like in manufacturing, you'd have these instances. And the reason diffraction is so popular is because it's a lensless technique, so you don't have the limitations of the lens and the resolution, and you can actually gain high resolution and high contrast reconstructions. So the first step would be to shoot these X-ray beams to get the Fourier magnitudes and then do phase retrieval, but this requires highly coherent X-ray beams, so that you cannot generate them in a standard CT scanner, but you need a synchrotron for that. So they're actually generated. This is a photograph of that I've taken when I visited the Paul Scherrer Institute in Switzerland, and I was actually amazed to see that this is, so you actually walk around here, and they have these beam lines, these huge beam lines. So it's like an arena that you walk into, and it's very expensive to actually do all of that. And why am I mentioning coherent diffraction imaging? Because actually, yeah, so one way of doing coherent diffraction imaging is actually very close to taking short-time Fourier transform measurements. So let me just say a little bit about this. So in one way to actually improve on coherent diffraction imaging is to create redundancy in the measurements to solve the phase problem. And that's called tachography. So you would have, before you actually shoot the X-ray beam on the sample, you would actually first have a pinhole that you slide around to create more measurements that are actually redundant in some sense. So, and that for us is something, so what we actually would gather at the end is something like the windowed Fourier transform magnitudes instead of just the Fourier transform magnitudes. Yeah, so let me now generate the formulate the problem more generally. So what we're actually asking is, given a measurement system, let's call it phi lambda, capital lambda being the index set, can we say something about stability and uniqueness when we're trying to recover the signal out of these measurements? So these would be the coefficients, but we have lost phase information. And another application is in audio processing. In audio processing, actually everything is in 1D, so it's maybe the most truthful to what we're doing right now. And one application in audio processing is the phase vocoder. So the phase vocoder is well, a method to actually modify an audio signal. So for example, you want to time stretch it or pitch shift it then what you could do is to actually go via the magnitudes in the short-time Fourier transform. Because if you just redistribute a short-time Fourier transform, you will not get another audio signal. But what you can do to be more truthful is to work only with the magnitudes, redistribute in time frequency, and then ask for an audio signal that would have such a spectrogram. And the other application that we've already mentioned is X-ray diffraction. What is important to note here, of course, is that as soon as we introduce those magnitudes, these absolute values, we are dealing with a nonlinear inverse problem or inversion problem. So a lot of the standard theory just doesn't work here. Okay, so the mathematical formulation would be, suppose I have a frame, maybe even a continuous frame. So continuous would mean that my index set doesn't have to be discrete. And well, I have to formulate this, of course, accordingly. And what I would like to have is that this quantity here, so for a discrete frame, it would be the sum, of course, of these coefficients squared, that this is lower and upper bounded by the energy of F, and we would call these the frame constants, the best possible constants A and B. And when we do phase retrieval, we have to account for trivial ambiguities. For example, in the real valued setting, we have to account for the plus and minus that we will never be able to recover, of course, when we have only phaseless measurements, or a factor on the unit circle in the complex setting. And also the distance, the definition of the distance has to reflect that. So of course, F and minus F, for example, will have distance 0, otherwise it's not meaningful. And phase retrieval would then be the inversion of this forward operator that acts from this quotient space into the according space in which we're collecting those coefficients. So the first thing I want to talk about is uniqueness. And to start with, I want to start with reviewing a very, well, by now, probably very classical result, but that hasn't been very well known at the time we were working on that. So, and this is really, it's very nice because it's so easy to formulate. So suppose you have a real valued band limited function, you know the sampling theorem, right? You know that you can recover the function out of its samples. So what if you don't know the samples, but you only know the unsigned samples? So you've lost, for each sample, you've just lost the sign, and you would still like to recover that function. So a result by Gabor says that you can actually do that. So suppose you have a real valued function that is band limited, suppose the bandwidth is B, then if you don't sample at the Nyquist rate, that would not be enough. You don't have any redundancy in here, but if you sample at least at twice the Nyquist rate, then you can recover the signal out of these unsigned samples. So this is what you need. Yes, and now I would like to start with the first, well, the first part of the results that I want to mention. So here I want to speak about time scale representations, mainly wavelets, but also at some point I will, I mean, one of the results also holds, for example, for curvelets. And I would like to tell you a bit about the uniqueness results here. So suppose we have a discrete frame, okay? And now we're only asking about sign retrieval. So actually everything is real valued. Both the signal F itself and the measurement vectors. So these psi lambdas, they're also real valued. And suppose they're even band limited, then you can actually observe that Gabor-Takacs result can be extended to dimensions, so to higher dimensions. And it already gives you that you can do sign retrieval on each scale. So suppose you have wavelets or curvelets, then you can recover on each scale already. But of course, that's not sufficient. You have to patch all the scale information together, right? So this is the first observation, that if you have something that is real valued and it is band limited, so you have a compact support in Fourier, then if you have a sampling set that is just, so you're sampling fine enough, let's say, it's not important how you come up with that at the moment, then actually you can do global sign retrieval for this function G. And yes, so if you also know that your frame has good, what we call good Fourier support overlap, so it's an open cover of the frequency domain, then you can recover up to global sign. So to give you an example, you can look at curvelets, and they have good Fourier support overlap. So this frequency tiling is exactly what we would need for this result. And you need some overlap in those regions to actually be able to like propagate the phase from one tile to the other, let's say. So to give you an example, in 1D, that will be Meilleur wavelets. They are band limited and they're real valued, so we can work with them. One can start with an orthonormal basis of Meilleur wavelets. However, we know that if there's no redundancy in the measurement system, then of course losing phase information is already an overkill. We can never make up for this loss of information. So the answer to this question is no, we cannot do that uniquely, of course. But what if we introduce some oversampling in the frame, some redundancy in the frame? And it turns out that yes, you can do that. So if your function is real valued and also exponentially decaying at infinity, then there is, you can come up with the rate that you need with the oversampling so that f is uniquely determined up to global sign by these frame coefficients. And similarly, you can work in 2D. So here's an example when you have a tight frame of second generation curvelets introduced by Candace and Donohoe. Again, a tight frame will not work, but if we oversample this tight frame, then we can actually find that we can do unique sign retrievability. And we can come up with the factors that we need for this redundancy. Yeah, so this is the factor here. We just have to, yeah, the delta 1 and delta 2, they come from the definition of the curvelet that we're using, this tight frame that we're generating, and the alpha 1, well, actually, delta 1, 1 over delta 1 times alpha 1 is the factor that comes up here. So this is why this is a bit different from alpha 1 and alpha 2. So this is all what we call sign retrieval.
Can I ask you a quick question? Sorry, is this over the redundancy factors both here and in the 1D case? Are these optimal, or is there a good reason for it not to be able to get all the way to 2?
Well, yeah, that's a good question. No, I don't think they're optimal. So I think so here, yeah. I mean, this is what you can calculate easily. We didn't try to optimize it, so I'm not sure.
Okay, thank you.
Could be, yeah. But I mean, these systems are very nice to do calculations in. Like you can actually compute the support, like the size of the supports and so on, and then come up with these numbers. But sharpness, I don't know, could be. Okay, but this is all sign retrieval. So actually, it's not an actual phase retrieval problem. So the signal is real valued and the measurement system is real valued. And actually, when you do the magnitudes, you only lose sign information. So this is inherently easier problem, of course. I mean, there is also, if you know the result, I mean, for sign retrieval, you actually have a necessary and sufficient condition for uniqueness, which is the complement property. And when you move over to complex, then you don't know anything. I mean, you don't know of a sufficient condition. You only know that there is a necessary condition. So that's why I think it's worth mentioning that there has been a result in the wavelet setting on phase retrieval and the uniqueness question, namely for Cauchy wavelets. So what are Cauchy wavelets? Cauchy wavelets are progressive wavelets, they're sometimes called, or analytic signals, which means that in Fourier, they are only supported on the positive axis. So they don't contain negative frequencies. And just to recall the wavelet transform, this is the continuous wavelet transform we would be working with. So X here is translation and Y is dilation. And then Malan and Walsburger, they have an interesting result, which tells you that if you work with the Cauchy wavelet, right, then knowing the wavelet transform on two lines in the complex plane, so sorry, two lines, AJ and AK make up for these lines. So two different scales, essentially. Then you have uniqueness of the phase retrieval problem, but what you recover is not f itself, it's called f plus. So f plus would be the analytic representation of f, and g plus would be the analytic representation of g plus. So does that mean? Well, it's a representation where you only keep the positive axis in the frequency domain. And for real valued signals, that's completely fine because you have symmetry in the Fourier transform. So if you only capture the positive axis, you can still determine your signal f. So in principle, f is uniquely determined by f plus, right? So there is no problem here. However, and that's what I would like to point out, if you have this up to global phase, it doesn't mean that you know f up to global phase. So this is shown here. If you have up to global phase the analytic representation of f, then the only thing you get for f is that it's related to g like this. So what I'm using here is that for a real valued signal, you have f plus is, so the real part of it is just f, the real valued signal, and its imaginary part is the Hilbert transform. And if you, well, if you try to understand what this means, namely that the real parts agree and the imaginary parts agree, then what you come up with is that f is equal to not a sine times g, but you get cosine alpha g minus sine alpha times hg. Alpha being the phase factor here. So that means if alpha is not a multiple of pi, then you don't have determined f globally, uniquely up to a global factor. So this is what I would like to emphasize here, because I have to say honestly, when I was reading it at the beginning, I was always like, okay, so we have unique phase recovery of the real valued signal, but actually that's not what's happening. So you have unique recovery of the analytic representation. And that's why we asked whether we can come up with a uniqueness result that actually give you uniqueness for the real value, for the real valued signal itself, so for f and not its analytic representation. This is what I would like to talk about next. And this is not up on the archive yet. We just submitted, I think, an hour ago. So I think it will be up very soon. And there we work with wavelets that have a finite number of vanishing moments. So just to recall what n vanishing moments mean, it means that you're orthogonal to the first n polynomials. And what we need is that it has a finite number of vanishing moments. So there is a non-vanishing moment L, okay? So this C should not be 0. And then we have that band-limited real valued signals, they are uniquely determined by their wavelet transforms, okay? So as opposed to having recovery of the analytic representation, we have now the recovery of the signal itself. And I would like to emphasize that the wavelet itself can be complex valued. So these measurements, they're completely complex valued. They can be entirely complex valued, and things work out. Okay, and one can take this further to a result on recovery from samples, because we have the band limitedness of f and g in there. So now the same assumptions. We have one non-vanishing moment here. Then if you take any sequence that goes to 0, okay, then you get unique recovery from these samples here. Okay, so this accounts for the bandwidth of, so omega accounts for the bandwidth of f. So this is how fine you have to sample in this coordinate. And then you just one thing that accounts for higher and finer scales. Oops. And the example I want to emphasize here is the Morley or the Gabor wavelet. That will be an example of such a wavelet. There's also the so-called linear chirp wavelet, but it's less common. Okay, so this is as much as I can say about wavelets and the uniqueness results that there are for wavelet phase retrieval. And what I would like to talk about next is the short time Fourier transform case. So now we have not a time scale representation, but a time frequency representation. So yeah, just to recap, the short time Fourier transform, we have it's like taking the Fourier transform, but first multiplying with a window. And this window, well, this translates over the whole real axis so that you capture different pieces of your signal. And important for phase retrieval, or at least for the uniqueness results, is that there is a so-called ambiguity function relation. So there is something that tells you that out of these measurements, VGF, absolute value, right? These are our phaseless measurements. We can actually, just square them, take the 2D Fourier transform. What we get is a pointwise product of the ambiguity of the signal and the ambiguity of G, the window. So what's the ambiguity? The ambiguity is just taking a windowed Fourier transform where you set the window to be the signal itself. So it's like, yeah, it's a quadratic representation of your signal. And what is important to note here is that once you know the ambiguity of F, you know your signal up to global phase. Okay. So if I take this formula, I know the left-hand side out of my measurements, and I need to work with the right-hand side. This is a pointwise product. So if I was able to divide by the ambiguity of G, then I would know my signal up to global phase. And that's why a condition for uniqueness is that there should be no zeros in the ambiguity. So if you have no zeros, or almost everywhere you have no zeros, then this actually works. So an example is the Gauss window. We know that the ambiguity of the Gauss window is a 2D Gauss essentially. Also the one-sided exponential doesn't have zeros in the ambiguity. Another example is Hermite windows. They do have zeros in the ambiguity, but these are sets of measure zero in the complex plane. So it works in an L2 setting. So this is rather restrictive, of course, that you have no zeros in the ambiguity. That's why we ask whether we can come up with other less restrictive assumptions on the ambiguity that would still allow a unique recovery of the signals. And what we ask here is, okay, maybe we have to restrict our signal class to come up with new results. So we're assuming that our signals are band limited, and we ask whether this helps in making the problem easier, in the sense that we need less to ask on the window itself. Okay, so this is, yeah, this is some work I've done with my PhD student, Matthias. So first of all, there is a real valued result. So if your signal is real valued, then all you need is that the ambiguity of the window is, so you take a line segment in the complex plane. Okay, so this is the line segment. You have 0 in the x variable and then minus 2b to 2b in the y variable. If you're non-zero on this almost everywhere, then this is enough for unique recovery. Again, you need band limitedness of the signals. And coming back to the result of Gabor-Thakur, you can actually use that to come up with a sampling result here. So if your window itself is real valued and has no zeros in Fourier on a line segment, so the example that we give here is the Gauss window. So the Gauss window is real valued, and its Fourier transform is another Gauss. It has no zeros. Then actually you have uniqueness from samples. And if you look carefully, then all we need, so we're not using any frequency information here. So we're setting frequency to 0, and we're able to recover from these samples. Why is that possible? Because these measurements here, if you think about it, they will be real valued if F and G are real valued. The complex valuedness only comes when you move away from the zero axis and actually modulate your signals at the window. And that's why it's not so, I mean, yeah, it helps us a lot that there is at least one line where the measurements are real valued, even if the rest is complex valued, to come up with such a sampling result. So this is actually the first result of recovery from the short time Fourier transform when you only have sampled data. Again, the signal, it has to be band limited and real valued. And in the complex valued setting, so suppose my signal is not real valued, but complex valued, but it's still band limited, that's important. Then what we need is that instead of just one line where the ambiguity, or one line segment where the ambiguity function should be non-zero, we need two lines on which the ambiguity function is non-zero, and these two lines have to be close to each other. And the closeness here being dictated to us by the bandwidth of the signal, so the Paley-Wiener space here. So again, non-zero almost everywhere on that line segment. So if you have these two line segments and you're zero almost everywhere on these two line segments, that will give you unique phase retrieval recovery for the signal F. And yeah. You can take this even further. So if you have a window that is not only non-zero almost everywhere, but it's actually strictly non-zero on this line segment -2b, 2b, and the closed interval, then you only need one line segment. So this is all analytic continuation that you can play around with. All right, so I think this is about it, about uniqueness. And yeah, now I would like to move on to the next question, which is stability. And stability here, yeah, there are a lot of bad news in stability, I would say, but there's also a little bit of good news. So, but the problem is inherently unstable. So that's maybe you shouldn't leave now. That's not what I'm trying to impose here, but the problem is inherently unstable. But let's see. So first of all, there has been very important and the first result on stability in this setting. So it's very worth mentioning, by Cahill, Casas, and Dobeshi in 2016, when they found that actually when you have a discrete frame and you're in infinite dimensions, the phase retrieval problem is never uniformly stable. So that's just, it doesn't matter if it's the short time Fourier transform or the wavelet transform, whatever it is, just take any frame if it's discrete. So if it's sampled data that you're collecting, the problem is never uniformly stable, unless you're in finite dimensions, of course. So one of the first questions we asked was, well, if you think about the wavelet transform or the Gabor or the short time Fourier transform, now this result is about sampled data. What if we don't sample data? So what if we have a semi-discrete frame where, for example, we only sample the scale? Or what if the data is not even semi-discrete, it's actually fully continuous? We have the full continuous wavelet transform in magnitude, or the full short time Fourier transform in magnitude. Does this bias anything in terms of stability? And just to remind you of what we mean when we say stability here, it's really strong stability. So we're asking for a lower and upper Lipschitz constant for this operator A phi. So the measurements, the distance in the measurements should be lower and upper bounded by the distance of the signals themselves. And what I would also like to mention here is the strong complement property. This was first introduced in the very famous paper Saving Phase by Afonso and his co-authors. And they actually conjectured that the strong complement property is a necessary condition for stability in finite dimensions. So we were definitely inspired by this. What does the strong complement property say? It says that if you take this measurement system phi, no matter how you split the index set into two parts, then one of the two parts, at least, should be a frame with lower frame bound at least sigma. So the sigma, there should be a universal sigma that exists such that this is true for any partition of the measurement system. And what we found is indeed the strong complement property is a necessary condition for stability. And then once you try to work with that, you can see that actually the SCP will never hold in infinite dimensions. So here it doesn't matter whether the frame was discrete or continuous, the SCP can just never hold as soon as you're moving to infinite dimensions. There is no such frame that satisfies the SCP. And that means that, yeah, I mean, if you take a wavelet transform, you increase the redundancy. I mean, I showed you examples where you can restore the uniqueness, but certainly you will not be able to restore stability as you increase the redundancy. And we did this in a very general framework. So this was a Banach space framework in which we worked. But yeah, just mentioning this. Now, what if we try to quantify this instability, trying to find out how bad it really is? And here I take the example of the short time Fourier transform where we have a Gabor, well, what we call a Gabor transform. So the window is actually a Gauss window. And we can do an explicit construction. It's actually quite intuitive. You take a Gaussian, okay, that we call phi here. It's the same Gaussian actually. And we translate it once by minus a and once by a. So here a is 5. And we take two signals, the one signal being the sum of the two bumps and the other one being the difference between the two bumps, okay? And well, once you do that, you get very similar, similar measurements, right? The measurements are almost agreeing. So here's the difference that I tried to plot. It's very small. And it will get even smaller as you move those two bumps away from each other. So essentially what you have in time frequency is two Gaussian bumps in 2D. And when you try to quantify this, so let's say, okay, suppose there is, at least for these two functions, let me find the stability constant, okay? As a function of A, the parameter A. Then you can actually calculate that this constant C1, it has to degrade at least exponentially in A squared. So this is where we use the term severe ill-posedness. And the other bad news is that these functions are so nice. I mean, this example is so simple that it also shows you that classical regularization will not work because you cannot come up with a good prior knowledge that you could use, right? They're both very nice functions. And they will have like whatever norm you're trying to use, like bounded variation or L2 or Best of space or modulation space norms. They will have very similar norms in that, in whatever you're choosing. So there is no good prior that you can, well, at least we were able to come up with. I also want to emphasize that, you know, if you open a classical textbook on inverse problems, then you will find that actually phase retrieval doesn't even qualify as an inverse problem in the sense that as soon as you're injective, the inverse is continuous on the range, okay? And classically, the definition would be that actually for ill-posedness, the inverse is not continuous on the range. Now, the problem being that this continuity is only in a weak sense, so you don't have uniform continuity, which means you cannot quantify. I mean, yes, you are close, but you cannot quantify it, right? It's in practice, it doesn't help you really. But just for completeness. So to give you an example, I mean, one example where injective is the Gabor phase retrieval problem. So if you have short time Fourier transform with a Gauss window, yes, you are injective, the range is closed, and the inverse is continuous on the range. Still, bad things happen. Okay, so it is not ill-posed in the classical sense. Yeah, and then what I want to show you is what we tried to do. I mean, okay, you have this inherent instability, right? So it is just like this, that whenever you have disconnectedness in the measurements, let's say in the time frequency or in the time scale representation, then you have this ill-posedness. So yeah, what can you do about it? And interestingly, when you consider audio signals, then when you have such disconnectedness in the measurements, it seems that when you multiply, let's say on this rectangle here, if I multiply this by a global phase, I will not hear a difference in the reconstruction. And the important part here being that it's disconnected to the rest. So if you try to do this on a connected region, like only on this part of the rectangle, for example, then you will hear something in the audio signal. And that's what has motivated us to try to find a stability result when you only do global phase retrieval on each disconnected component in time frequency or time scale. Okay, so this is what we call maybe semi-global phase recovery. So you look at the time frequency or the time scale representation, you identify the regions that are disconnected. Disconnectedness just meaning that the values here are very small, the magnitudes here are really small. And to make it a more realistic setting, you have to allow like small holes, small regions in which the measurements can also be small. And you only want to do recovery like this. So on each region, you're asking for global phase retrieval. So one can introduce atoll functions. So atoll functions, you're looking at a domain in which you have so-called lagoons. So in these, the measurements can be small, but here they're lower bounded. On the gray shaded region, they have to be lower bounded. So by this little delta. And then you can actually show stability if your measurements are, well, they're up to a weight factor, they're holomorphic functions. So this is true for the Gabor transform, for example. If you take the short time Fourier transform with a Gauss window, then it is well known that there is a weight function eta, so that if you multiply, yeah, up to this sign here, but if you multiply your short time Fourier transform by it, then you'll get a holomorphic function on C. Okay. And the same can be done, or similarly, for the wavelet transform. So for the wavelet transform, there is the Cauchy wavelet transform that we've mentioned, and actually in Malan and Walzburger, they actually employ methods for entire functions, a theory of entire functions, to come up with their results. And this can also be used for stability. There is also a weight function that you can multiply the Cauchy wavelet with, so that you get something that is holomorphic on the upper half plane. Okay. Why am I mentioning this? Because we have a stability result for holomorphic measurements. It tells you essentially that if you have that F1 and F2 are holomorphic up to the same weight, that's important, that it has to be the same weight, then you get a stability result. Okay. This has been further improved. So there is work by Gross and Rathmeier. They actually introduce for each function, they can come up with quantity related to the connectivity of the measurements in time frequency. So they take the short time Fourier transform and measure the connectivity with something they call, or is related to, the Cheeger constant. And that's how they can quantify the stability constant here much better. Okay. Yeah, and finally, I want to mention the finite dimensional case, because I told you that in infinite dimensions, the problem is always unstable. And And also you can say that actually in finite dimensions, the problem is always stable. This has also been mentioned by Candes and his co-authors. However, the problem is just very ill-posed. So here's an example by Cahill, Casas, and Dobeshi, where they consider this example that Gaurav Thakur was working with, namely the recovery of band-limited functions from their samples. And you can create so yeah, I mean, you can, for the Paley-Wiener space, you can come up with a frame, right? And then use finite dimensional approximations of this, of the Paley-Wiener space. And what they come up with is they can construct a family of functions in that each lie in these finite dimensional spaces, so that the stability constant degrades at least exponentially in the dimension. So yes, the problem is stable, but of course it's very ill-conditioned, and you have exponential growth here in the dimension. So one has to think about the stability also in the finite dimensional setting. And one thing we've worked with is to think about the discrete Gabor transform. So you have the short-time Fourier transform, but here now in the discrete setting, you have a signal that is of length L, and you're collecting its windowed or short-time Fourier transform measurements in the completely discrete setting. And the idea was to replace the atoll functions by graph formulation. So here we would have a threshold delta, and this is the full signal, right? But we would actually say that this is one island and this is another island in time. And we would only aim at recovering this piece and this piece up to global phase individually. And the way to do this, or to show that there is stability, is to actually connect like this part of the data with and this part of the data, and not try to actually propagate phase from one region to the other. So yeah, you can show, and here what we need again is that X and Y have a bandwidth, a certain bandwidth of a certain bandwidth B, and then we can say that if they have K-connected components, we can come up with a stability estimate like this. However, the stability constant will depend on the size of the ambiguity of the window on certain segments. Yeah, so this is, I think, the last thing I wanted to show you. Yeah, so just want to mention at the end that there are a lot of exciting questions one can think about. I mean, for example, the stability results I've mentioned for the short-time Fourier transform. So also the extension that Gross and Rathmeier have done, they all need the window to be a Gauss window. And one question is, of course, what happens for other windows if the window is not a Gauss window anymore? Also for the wavelet transform. So there is a result, I should have mentioned this, there is a result by, of course, I forgot the authors now, that tells you that the Gauss window is the only window that will generate such holomorphic measurements in the short-time Fourier transform setting. And the Cauchy wavelet is essentially the only wavelet that will exhibit this holomorphy in the wavelet transform. So there are no other classes of wavelet transforms or short-time Fourier transforms that give you this holomorphy. And this, the techniques used, they always need this holomorphy. So the question would be, what happens for more general transforms? Yeah, also on the algorithmic side, I think there are a lot of interesting things. I said that there is no good prior. And so generally speaking, just doing regularization will not work here. There is one algorithm, it's called phase gradient heap integration for the short-time Fourier transform, where you actually do this reconstruction on atolls, which is exactly what we would like to do. But to do one reconstruction on the atoll, what they do is to use the holomorphy again. So they use Cauchy-Riemann equations to propagate the phase. And again, it's not clear what you would do if your window is not close to a Gauss. And also, you know, leaving this framework of time scale or time frequency representations, having something for general frames where you could have a good tractable necessary and sufficient condition for uniqueness, for example, and so on. So yeah, I think it's still a very exciting field, and I would like to thank you for your attention. Here is a link to the references. As I said, there is one that is still not up, but hopefully tomorrow or something. Thank you.
Thanks so much, Rima, for the great talk. So we'll open now the floor for questions. The panelists can just unmute themselves and ask, and participants, please write it on the Q&A, and we'll ask the questions. Okay, so while we wait, I have
a quick question, I guess.
Oh, go ahead then, yeah.
So Rima, you mentioned that counterexample to stability, where you have like an even and odd version of a function, and then the stability constant is pretty bad.
Mm-hmm.
What happens if you restrict to only non-negative functions?
Yeah, you can essentially play that game in frequency. So you could have a gap in frequency, right? And in the frequency gap, I mean, in frequency, you flip one of the components, and then you get the same problem, I think.
I see.
Yeah, I have a related question, actually. Is there a natural way in which to measure how bad the function is? In this sense, like it feels like the measurements start being more and more unstable when the bumps get further and further away. This seems very close to the issue that that people attempt to solve with things like optimal transport and Earth movers distance and so on. It's not quite the same. Like, yeah, I couldn't see any way of actually relating them, but it feels similar. At least the issue that is trying to be solved. Is there any natural way of like quantifying how bad the function is in this sense? Like that's natural.
Yeah, I mean,
I would give you, yeah.
I think what Gross and Radmayer do in the spectral clustering approach essentially gives you a good quantity that tells you whether it's a bad function or a good function. I mean, under the assumption that you're working with the short-time Fourier transform with a Gauss window, at least. So this is essentially a quantification. So if this constant, you can calculate it just out of the measurements. And I don't know if it's bad if it's small or if it's bad if it's large, one of the two. Then, I mean, yeah, I think it's right now the best way to quantify this. There's also a new paper that I unfortunately haven't really had the time to study yet by Ingrid Dovishi and other co-authors. They also studied the stability question, but on a local level. So I can't say much about it, but it could be that they do more of this quantification.
Hey, thanks. And so okay, I'll ask another question.
Yeah.
What are the competitive algorithm, like what do the algorithms look like? Like if you were to run an algorithm for these problems, what are the sort of the classical things to do, and what do they look like? And do they have any guarantees? I imagine maybe not because of the issues with stability.
Yeah, that's a good question. So, I mean, the one I like the most, at least because it's, you know, it's non-iterative and it's very, well, at least it really stems from the mathematics that you would do, is this phase gradient heap integration, right? But of course, it also means that you're, you know, if you're, the errors, you're just propagating them too, right? Because you're walking from one node in time frequency to the next. And things get bad when you get, so when the magnitude is close to zero, so when the magnitude is small, that's when things get bad. And then you propagate, you get to propagate these errors. So I don't think it has any guarantee. And then there are all these iterative algorithms that I personally haven't really worked with a lot. But that, I think, I mean, they work well, but about guarantees for this on the algorithmic side. So, yeah.
Right, thanks. So